Okay, in Objective 3, we looked at what is going to be a new shape for most of you, which is called an ellipse. An ellipse is something that you have seen before, but I'd say up until this point, you've probably always called it an oval. It's a very special kind of oval. It's the set of all points in a plane, such that the sum of the distances from any point P, so say we were to call this P here, to two fixed points, which are called the foci, is a given constant. And so my foci are here, so we'll call this F1 for the first foci, and here F2 for the second foci. And these distances here, if we were to call this A and this B, if I were to add those two distances, A and B, no matter where this point moved along this ellipse, the sum of A and B, which will now be switching as well, right? Think about it. This P moves, that A is getting longer, this B is getting shorter. We move to the right, vice versa for the left. But their sum of whatever that A and B happen to be, it'll always be the same. Okay, the foci of an ellipse, they are on the major axis, which is the longest axis. That is important. We will call the major axis always. Never x-axis or y-axis, because actually that changes. The major axis could be either one. Just depends on the ellipse. Okay? An indicator of the shape of an ellipse, whether that ellipse is particularly elongated or particularly round, is called its eccentricity, or E. And it's defined by this equation right here, E equals C over A. Now one thing, before I complete my circle here, that you need to know is I almost will never call it A. I don't like A. A is used in a lot of ways through conics. I've even used it here inside of the picture to like denote a distance. We use A and B for Pythagorean theorem. Like it's just, I feel like A is overused and it doesn't really help us know what we're actually talking about. So I will always call it big R. The reason I will call it big R is because this number down here will always correspond to one of two radii. An ellipse always has two radii, a shorter one and a longer one. And whichever one's the bigger one, that's what big R is. Little r will be the littler one. And so I like big R because it does represent what we are actually looking at, which is the big radius. Whatever the big radius is, that's what goes down here. C is going to be the distance to the focus. Just like with parabolas, it's exactly the same as parabolas. And A, which again I'm not going to call A, so I'm going to call it big R. And big R is the distance to the vertex from the center. Vertex, okay, vertex I didn't put into the notes, so we're going to add that. Vertices, there are two of them, and they are always on the ends of the major axis, never the minor. Vertices are endpoints of the major axis. Okay, so some other little pieces here. One, this is your descriptive form of your ellipse. It has a lot of similarities. Some of the ones you've looked at, you still have that x minus h squared from the circles and the y minus k squared from the circles, so you'll still have an hk as a center, what zeroes out those two components. One small difference is you will have fractions with a 1 on the other side. This will always be 1 for the record, even when we get to hyperbolas, which will have a very similar equation. If it's not a 1 over here, we'll need to get it to say 1. Okay, you still have your focus, which is your C, right? Or I should say it's the distance to the focus. Now, we don't have a 1 over 4c for this one because we are in a parabola, so we find our focus a little bit different, which is our big R squared minus our little r squared, which is our c squared. Okay? Big R being whichever radius is bigger, little r being whichever radius is little. is smaller, right? Okay, which is detailed here. And then two other things here, your major axis. So your major axis is what goes kind of between the two vertices. It's what is made up by the larger r, your bigger r. And so since the radius is only half, the major axis would be 2 of that radius, right? 1, 2. Your minor axis is the littler radius, and again 2 of those, because radius again is only half. So 1, 2. Okay? So here we go. Graphing. We've got some steps over here. Putting it into descriptive form. We'll always start there. Sometimes we'll involve completing the square. Sometimes we'll involve getting this 1 to actually say 1. So may need to complete the square. May need to divide. To get 1. You'll find and graph the center, your HK. You'll then do your 2 radii, and again this A and B. I actually won't be calling them A and B. I will be calling them X sub r for X radius and Y sub r for Y radius. Okay? We're going to find C, which will come from big R squared minus little r squared equaling C squared. We'll graph our foci, which will come from moving C units from the center along the major axis. Remember, it will always be along the major axis up here. Your foci, the foci of an ellipse are on the major axis every time. Okay, so you always start here and you'll go C to one focus, C to the other. Okay. You'll label your vertices, which again are always the endpoints of the major axis. I wrote that up here. And then you'll find your eccentricity, E equals C over, and again I'm not going to call it A, I'm going to call it big R. Okay? And so here we go. We're going to write each equation in descriptive form, identify the characteristics, and then sketch it. Okay, so descriptive form. I need to see it factored, and I need to see it equaling 1. Factored, good, so I don't have to complete the square. Equals 1, good, so I don't have to divide. Step 2, I need to find and graph my center. So go ahead and take a moment. What would be my HK? Okay, my HK in this case, my center. My H would be whatever zeroes out the X, which this is just X squared, so that'd be 0. My K would be whatever zeroes out the Y, which would be positive 2. So we're at 0, 2, which is there. Okay? We then need to find our radii, so we can graph those. XR and YR. Okay, well XR is the number being squared underneath my X. So in this case, the number being squared underneath my X is 4. 4 squared. And so my X radius is 4. My Y radius is whatever number is being squared under my Y, which would be what? It would be 5. And so that gives you your 4 additional points. In the X directions, I'm going to count 4. In the Y directions, I'm going to count 5. So in the X directions, count 4. 1, 2, 3, 4. 2, 3, 4. In the Y directions, count 5. 5. 1, 2, 3, 4, 5. This was an inequality. We'd have to check if we were solid or dashed. We aren't an inequality, so we're good to go. And there's my ellipse. Okay. Okay, so then my characteristics, the rest of my characteristics here. Okay, I found my center, I found my radii, which will allow me to find my vertices. Let's do vertices next. Vertices, remember, are always at the edge of the major axis. In this case, my bigger axis is up-down, so that's a vertice, and that's a vertice. This vertex down here is at 0, -3. And this vertex up here is at 0, 7. Okay, center, vertices. I can find my lengths of major and minor axis. My major axis is always 2 of my bigger R. In this case, my bigger R is 5, so 2 5s would be 10. I can also see that by counting, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 long. Minor axis is 2 of my little r. In this case, my little r is 4, it's smaller than 5. And so 2 of 4 would be 8, or again, I could get that by counting. 2, 3, 4, 5, 6, 7, 8. And so then the last things I need to find are my foci and my eccentricity, both of which require me to find C. And so that brings me here to step 4. When I want to find C, C squared is always equal to your big R squared. My big R in this case was 5, so 5 squared would be 25. Minus my little r squared, 4 squared, which is 16. So C squared is 9, which means C would be 3. Well, actually, it'd be positive and negative 3, but we're talking direction here, a distance for my foci, so the negative 3 doesn't really change the distance to my vertex. The distance is a distance of 3. Right? We don't ever run like -3 miles. We run 3 miles. Whether it's forwards or backwards doesn't matter. We run 3 miles. So this is a distance here that we're talking, the distance to my foci. Okay? And so for my 2 foci, I'm going to go 3. Remember one more time, foci, always, always on the major axis. So in this case, I'm going to start here and I'm going to count 3 either way on the major axis. 1, 2, 3. So there's 1 foci. 1, 2, 3, there's the other foci. And so my 2 foci in this case are at 0, -1, and 0, 1, 2, 3, 4, 5. And we've got our 2 foci there. And then our eccentricity, our E, is always equal to my C, which is 3, over my big R, which in this case was 5. And we've got our attributes. Okay? Okay, with each successive one then, I'm going to encourage you to pause the video, give it a shot, restart it when you're ready. I will say the next 2 take slightly different forms of turning them into descriptive form. So maybe if you look at it, you're like, I'm not sure how to get that in descriptive form. Maybe watch the descriptive form piece, but then pause it and see how many of these attributes you can get on your own, restarting the video as you feel like either you are stuck or you have an answer to check whichever one, whichever boat you find yourself in. Okay? But number 2, starting with number 2, the descriptive form, this is the first time we're actually going to have to manipulate. One second. Excuse me, sorry. So, manipulating this one. Currently, we don't have any factoring we have to do. We don't have like an x squared and an x, so we don't have to complete the square, but we don't equal 1. And so this is that second one. You may need to divide to get 1. And so in this case, that would mean dividing by 100. So then you'd work your way along, okay? If I reduced this, 4 over 100 reduces to just 25 on the bottom. 25 over 100 reduces to just 4 on the bottom. And 100 over 100 is 1. And we're now technically in descriptive form. Yeah, we don't see our xr squared, but if that really bothered you, you could always rewrite it, because 25 is the same thing as 5 squared, and 4 is the same thing as 2 squared, but we are in descriptive form here. Okay, so at this point, I'd encourage you, like I said, pause it, see how far you can get, restart it when you're ready. Okay, so HK, in this case my center, my HK, would be at 0, 0. What zeroes out the x, what zeroes out the y? My XR is the radius underneath my x. So in this case that would be 5. My YR is the radius underneath the y, which would be 2. And so I know this is my big R, that's my little r, because 5 is bigger than 2. Okay, so I'm counting 5 in either direction, x-wise. I'm counting 2 in either direction, y-wise. So x-wise, 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Y-wise, 2. If we were in an equality, we'd be checking to see if we were dashed or not. Or not in an equality, so we're good to go. And there's my ellipse. Okay, all of its attributes then. Okay. Vertices. Vertices, again, are always at the end of the major axis. So those are my two vertices. And they are at 5, 0 and negative 5, 0. My major axis, always 2 of my big R. My big R in this case was 5, because that's bigger than 2. 5. 2 5s is 10. Or again, you could count it. Minor axis, 2 of the little r. So 2 2s, which would be 4. Okay. Now we need our C to find our foci and our eccentricity. So C squared is always equal to your big R squared minus your little r squared, just like we have here. Right? So let me box that in. So my big R squared, big R is 5, squared would be 25. Little r squared, little r is 2, squared would be 4, which is 21, which makes C, again, technically speaking, plus or minus root 21, but again, we're talking distance to our foci here, and so we're just going to write root 21. Okay, so my foci, always on the major axis, just like the vertices, always on the major. So we're root 21 either direction. Okay, so how much is root 21? Okay, well, root 21 is pretty evenly between root 16 and root 25. Root 16 is 4, root 25 is 5. Which one is it slightly closer to? Slightly closer to root 25. Right, it's only root 4 away from root 25 as opposed to root 5 away from root 16. So this is about halfway, but slightly closer to 5 than to 4. Okay, and so we're going to go about halfway between 4 and 5, but slightly closer to 5. So 1, 2, 3, 4. Here's about halfway, slightly closer to 5. 1, 2, 3, 4. About halfway, slightly closer to 5. So my foci are about right there. Okay, those two foci are at positive root 21, 0, and negative root 21, 0. And then your E, your eccentricity, is C over big R. My C is root 21 over my big R, which again was 5. It was at this point in class that some people asked, what is eccentricity exactly? Like I know up above we said that it helps as an indicator of the shape of the ellipse, but what is it exactly? And I will come back to that at the very end of these, but I want to do 2 more examples before we address that idea. Okay, so hold on to that thought if you have that question. Okay, turning the page, we're going to do 2 more. We are not going to write equations for ellipses today, so we're just going to do numbers 3 and 4. Again, my recommendation, pause, try to get as far as you can on your own, restart it as you're stuck, And if you're only stuck on like one little part, if I explain that part and then you're like, oh, okay, I got it, then pause the video again and try to keep going with that one little helpful hint. But you need to take ownership for this, right? Be practicing this on your own. Okay? So, number 3, we do have to complete the square. Okay? So, pulling, or I should say restructuring, we have our 36x squared and our 144x. I'm going to factor 36 out as I do that. So x squared, 144 divided by 36 is 6. Let me double check that real quick. Nope, it is not 6. It is 4. Yes, it is 4. 4x. There we go. We've got our 9y squared and our 54y. Factoring out 9, we'd have y squared plus 6y. And then our 99 is going on the other side, adding that 99 over. Okay, so half of this would be -2. Squared would be 4. And so technically speaking, what I've added in here is 144. Half of this would be 3, squared would be 9. So I've added in here an 81. So this is 36 times x minus 2 quantity squared plus 9 times y plus 3 quantity squared equals 99 plus 144 plus 81 is 180, which is 324. I think, let me double check that. Yes, 324. And then like we did on the last example, we do need to divide by 324 to get this into its descriptive form. And so we have x minus 2 over 9, y plus 3 squared over 36, and 1. Which this is the same thing as 3 squared. This is the same thing as 6 squared. Okay? And so then let's find our pieces. We've got our center. Again, pause the video if you feel like you've gotten past something and you want to try it on your own. Pause the video, try things on your own. Own this. Right, center. HK, my h in this case would be +2. My k would be -3. So we're down here. Oh, and this one is going to go slightly off the graph down below, but just, I think, 1 if I remember correctly. My x radius in this particular case, the radius underneath the x, which would be 3. My y radius, the radius underneath the y, which would be 6. So I'm counting 3 each direction for the x's, and 6 each direction for the y's. Oh, looks like it goes down 2 actually. As an inequality, we'd be checking our sign. We aren't an inequality, so we can just connect. And we've got our ellipse. Okay. Attributes, vertices. Vertices, always, always, always on the major axis. Those are my vertices. These are at 2, 3. And 2, -1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Major, minor axis up next. Okay, my major axis in this particular case, 2 of my big R. My big R is 6, and so 2 of my big R would be 12. Minor axis, 2 of my small r. My small r is 3, so 2 of that would be 6. Okay. I need c for my foci and eccentricity. So c squared equals my big R squared, so 36, minus my little r squared, 9, which is 27. So C is root 27, or 3 root 3. I like root 27 for graphing. Okay? Okay, so foci, that's where I'm counting. Remember, foci always, always, always on the major axis. Root 27 is a little bit more than 5. Root 25 would be 5. This is maybe like 5.2-ish. Okay, so we're counting like 5.2, roughly speaking. 2, 3, 4, 5, and a little bit. 1, 2, 3, 4, 5, and a little bit. So those are my foci. Okay, their coordinate points. Now, this is just a kind of a helpful way to write their coordinate points, especially once kind of weirder roots get involved. One thing you could do is this. The foci always originate from the from the center, right? It's always where we start counting from. And so if I took my center, my 2, -3, and I started there, and then I asked myself, okay, which one of those coordinates changed for these foci? Did my x stop being 2, or did my y stop being -√3? Well, for these foci, we were going up and down, meaning the y was changing, but the x wasn't. So that x could actually stay the same. The y was changing, and it was changing by root 27. I was adding root 27 to it, and I was subtracting root 27 from it. And so one of the fastest ways of writing this would be to write the coordinate point first with the plus root 27, and then with the minus. Or you could do plus and minus root 27. Or plus and minus 3 root 3. Okay? It's a little way to kind of shortcut your focus, especially once the C is kind of a weirder C that way. Start with your center, and then just ask yourself, does this change the x? If so, put it with the 2. Or does this change the y? If so, put it with the -3. And then last but not least, we have our E. E equals our C, which is our root 27, or 3 root 3, over my big R, which was 6, which if you'd like to reduce that would be root 3 over 2. Okay? Okay, one more. If you haven't already, pause the video. Just make sure you're aware this one's an inequality. Here we go. Completing the square, we've got to group our x's here. I'm going to factor out a 4. So we have x squared minus 6x. Our y is grouped, going to factor out a 9. Y squared minus 10y. Subtracting that 225 over to create negative 225. Half of -6 is -3, squared is 9, which means I've just added a 36 in. Half of -10 is -5, squared is 25. I've just added a 225 in, which means this first one factors to x minus 3 squared. The second one to y minus 5 quantity squared. And at the back, negative 225 plus 225 will cancel, leaving me with 36. Dividing by 36, we get our descriptive form. X minus 3 squared over 9, which is 3 squared. Y minus 5 squared over 4, which is 2 squared, and our 1. Okay, center HK. My H is 3, my K is 5. X radius underneath the X is 3, Y radius underneath the Y is 2, so I'm counting 3 in the X directions, 2 in the Y's, and then this one is an inequality, so what are we here? We are dashed. For shading, if I were to test a point, maybe I tested 0, 0, I'd get 9 over 9, which is 1, plus 25 over 4, which is 6.25. So this would be 7.25 is less than 1, which is a false statement. So 0, 0, which is outside of my ellipse, is false, meaning I'm not shading out here. Where I'm shading is inside. And there's my graph. Okay. Attributes. Vertices. Vertices always at the end of the major axis. Always, always, always. These two vertices are at 0, 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Major axis. 2 of the big R. Big R in this case was 3, so this was 6. Minor axis. 2 of the little r in this case was 2, so 2 of that would be 4. We need our c for our other stuff, so c squared is your big R squared, 9, minus your little r squared, 2, which means c squared is 5, so c is root 5, which is a little bit more than 2. Okay. We're looking at a little bit more than 2. Remember, foci, always counting on the major axis. Sometimes that's up and down, sometimes that's side to side, doesn't matter. Foci and vertices are always on the major axis. So my 2 foci in this case, you wanted to use the strategy we just talked through. You'd start with your center, 3, 5. And then you'd ask yourself, okay, well, which one was actually affected in this case? Am I going to be making that root 5 get added to the 3 or to the 5? In this case, my foci still have the same y value, right? Both foci still have a y value of 5. So that's not the problem. The 3 is what changed. The 3 I added a root 5 to and subtracted a root 5. And so you'd put both of those in there. Or again, you could put 3 plus or minus root 5. And then last but not least, our e, which is our c, root 5, over our big R, which in this case our big R was 3. Okay? Okay, final piece here. I said I was going to come back to it. What does that E mean? Okay, I'm going to go back to the first page and add it in here. Our E, what the E is doing is indicating the shape of an eccentricity. Okay? The more oval the ellipse, you're looking at an ellipse and you see that it's really oval. The more oval the ellipse, the closer E gets to 1. The more round, or the more circle the ellipse, the closer E is to 0. Actually, you're going to see that it's a little bit more true that it's closer to 1/2, but it's that idea that the further you get from 1, the more round you're getting. So maybe that's what I should say. The more circle the ellipse, the further from 1 E is. That would probably be a little bit more accurate. But I like this idea of comparing it to 0 because the number helps you remember this shape. The more oval, the more elongated you are. So say we had a really elongated ellipse. the closer to 1 E is. The more round you are, the closer to 0 E is. And so I like that kind of like visual representation, just to help you remember kind of which one is which. And so you can see that even in what we've done. Say you were to compare 3/5 and root 21 over 5 in these first two examples. 3/5 is about what is a decimal, not about what is it as a decimal. Excuse me, 0.6, right? Root 21 over 5, I don't even know what that is, but that's pretty close to 1. Let me plug it in here. Root 21 over 5 as a decimal is 0.9 and some numbers, but if I were to round it, 0.9. 0.6 versus 0.9. 0.9 is a lot closer to 1 than 0.6 is. And so you'd expect this one to look a lot more elongated, a lot more oval. 0.6 is not as close to 1, and so we would expect our 0.6 to look more circular than our 0.9 would. Closer to 1, the more oval, more elongated. Closer to 0, the more rounder you get. And so look at your two graphs. 0.6, which was the one that was further from 1, does look a little bit more round than our 0.9 does, which definitely looks very oval. Okay? That's what eccentricity is. And again, you can see it even on the last two. It's just not as well, right? Our root 3 over 2, which as a decimal would be about 0.87 versus our root 5 over 3, which is kind of 0.7. So this one, 0.87, should be a little bit taller, a little bit more elongated, I should say taller. Should be more oval-like, more elongated than our 0.7 does. Not by much, but a little bit. And sure enough, if you look at it, this one definitely does look like it has a little bit more of a stretch to it. And this one has a little bit more roundness to it, because this one was further from 1 than this one was. And so that's what the E is it's just generating that, or indicating that general shape. Okay? And those are ellipses.